And the best we can hope for is Jones-optimality, which is after Neil Jones. And in the past, that has been hard to come by. And I'm here to persuade you that we can design and implement a partial evaluator that is Jones-optimal, self-applicable, and statically typed. And I have a few things I want to cover to support that. This is the new idea, which is specialization-safe normalization. And so I'll get into defining that. Then I will talk about how we type check the new partial evaluator. And then finally, I will show experiments with a range of combinations of both ways of representing programs and ways of measuring optimization. And so let's begin with establishing a baseline for what we're going to improve on. So a partial evaluator is a program specializer, and the idea is that if we have a program P, I'm going to talk about the representation of P as P bar. Then what mix the partial evaluator does to this representation of P bar is if you supply one of the arguments, say X, one of P's arguments, then the partial evaluator will create a specialized version of P, which will then take the remaining arguments. And the idea is that the specialized program running on the remaining arguments will run just as the original program did on X and the remaining arguments. And as you can see, I'm going to do lambda calculus. Today it's all about pure lambda calculus, so all the equivalences here are going to be beta equivalents. And so already in the 70s, Futamura observed that if your partial evaluator is self-applicable, which means that it's in particular written in the language that it partially evaluates, you can self-apply it and you can do things like generating a compiler generator, and later people found the fourth Futamura projection that Peter Sestoft called the mix point, that one can also self-generate the compiler generator. So all of that is good, and we definitely want this to happen. And then let's look at a particular instance. So I'm going to go with Torben Mogenson's partial evaluator from the early 90s, pure lambda calculus, self-applicable, achieves all the Futamura projections. So what he did was that he used church encoding of programs, and then he used beta normalization as his partial evaluator. So you take your stuff, beta normalize, make sure you get a representation, and if your program representation is church encoding as he used it, it will totally work. And then the question is this Jones optimal? And the answer is no. And so to approach what's going on with that, let me make progress towards defining Jones optimality. And so a key concept in Jones optimality is a self-interpreter. So again, self for an interpreter that is defined in the language that it interprets. And what a self-interpreter does is that it, in this definition, peels off a layer of representation. So if we start with P, then we represent it as P bar, then you, the self-interpreter, will peel off and get us back to P. And then what Jones optimality is talking about is that the partial evaluator should be able to specialize away all the work done by the interpreter. So we know that interpreters have overhead, and the partial evaluator should be able to get rid of all that overhead. And the way this is phrased in Neil Jones's definition is that if you start by partially evaluating the self-interpreter with respect to a program, then the specialized program should run at least as fast as the original program, and that is on any input. And so, so it means we definitely have to, as part of this project, we definitely have to program self-interpreters, and we have to write a partial evaluator that is good enough to specialize away their work. So now we come back to this point, is Torben Mogenson's partial evaluator Jones optimal? And the answer is no, and here's an example. So here's some code. It happens to do some math with church numerals, and if we get all the way down to F, in the middle of the page, it takes two arguments, X and Y, and if we supply the church numeral 2, then this reduces in 82 call-by-value steps. But we could also run Torben Mogenson's partial evaluator and specialize this F to to have X equal to church numeral 2, and then we get the code at the bottom, and that code normalizes with call-by-value steps, 89 of them, 89 call-by-value steps. So that was a slowdown. And you can see why, because the code at the bottom has a duplication of square and y. So somehow duplication happened. And so duplication is the culprit here. It's actually duplication that we're going to fight. And you know what's going on. When we have a beta read X, you never know. Maybe X is duplicated, and if E2 has work, we may end up duplicating work. And so here we have the tension. This is really at the core of the problem that we are addressing. On one hand, we need to control duplication so that we never slow things down. And on the other hand, we need to not control duplication too much so that the partial evaluator can do the work and in particular achieve the Futamura projections. That's our benchmark, if you like. So the key definition, it's like the spec of what is this partial evaluator going to do is this definition here. So we have this reduction relation, and eventually I'm going to use a reduction relation like that to replace beta reduction in Torben-Mogenssen's partial evaluator. And so what we want this reduction relation to be is specialization safe, as we call it. And it has to be specialization safe with respect to some time functions that measures how much time does it take to compute. And so the idea is if we take some specialization safe steps, then whatever code we end up with should be at least as fast as what we had before, and that is for all inputs. And so we need a specialization safe relation like that, and let's look a little bit into some particular cases that we definitely want. So here's one. Here we have a read X. It applies to tertiary numeral 4. And there's no duplication of work here, so that one should be specialization safe. Then we have this one. So here we have a read X at the top level there, where if we start contracting that, we would be duplicating the work of square of n2. So that one should not be specialization safe. Then there's this one. This is really a variation of example 2, where, again, there's a very high risk of if we contract this read X, we're going to duplicate some work of n applied to n2. So that should not be specialization safe either. Then there's this one where, as you notice, Y is only occurring once. And so even though there's some F applied to n2 going on in the argument, there's no risk of duplicating anything here. So that one should be specialization safe. And then my final example is this one. So if we start reading from the left, you see lambda n, and n occurs only once, so that seems good, but n occurs in the body of lambda m. And of course, lambda m may end up getting duplicated. And so if there's any kind of work associated with n, then we may end up indirectly getting n duplicated anyway. So this one should not be specialization safe. Okay, so with all that in mind, now we're going to take a crack at controlling the duplication. So we go with this grammar here, where we have normal variables for the form x, and then we have affine variables of the form x with a little circle. And so it's affine in the usual sense that x is allowed to occur once or not at all. And in addition to that, these affine variables can never occur in the body of a nested lambda abstraction. So that is the key. So maybe you know some papers that do affine variable lambda calculus, and so this is our version where never use an affine variable in the body of a nested lambda abstraction. And so we have a concept that defined what I just said of what you're allowed to do, some notion of well-formedness. And just to give you a few examples of what it looks like, Mogenssen, of course, had a self-interpreter, so we can talk about what it means to do Jones-optimality. Here it is. And as you can see, there are 3 lambda-bound variables involved, and all of them are affine according to our definition. In each of the cases, the variable occurs once, and it never occurs inside a nested lambda abstraction. So that's a totally good term there. And the next 2 are good too. And I bring up this example just to hammer home on the point that there are multiple ways of annotating a lambda term, and here are 2 different ones. And we have a little algorithm that infers annotations, and we always go for the maximal number. And that turns out to work very well for us. And so I just want to note that I'm going to define a reduction relation on these terms, and the reduction relation will really treat these 2 terms differently. Maybe whether this example or not, but in general, they will that reduction relation will treat them differently depending on how they're annotated. We always max out the annotations. So here's now the one slide that is at the core of the talk, which is our specialization-safe reduction relation. And so the way to think about this slide is that it does more than call by value, and you can see that because the first 3 rules up there is call by value. And it does less than full beta, and we do that because we definitely don't want to get a duplication of work. And then if we go a little bit further, rule 6 and 7 on the right, they allow reduction under lambda, so that is fine. Rule 4 is like the key rule when we think about affine variables. That's the one that says if x is an affine variable, there's no risk in duplicating work, so the argument can be any e prime. And then, in a way, we could stop there, except that we can't, because we have applications where our partial evaluator sometimes runs into need to do rule 5 as well. So in some applications, rule 5 is needed, some other times it's not needed. But rule 5, as you can see what it says, is that if we have a normal lambda variable x there, we want to apply that regex to a variable y. And that is fine, because the normal variables, as you can see, are treated as call by value. So y is eventually going to be replaced by a value. So there's no duplication of work by risked by contracting that regex. So that is our relationship. That is what we are going to build in to our partial evaluator. And we have theorems. Specialization-safe reduction preserves this concept of well-formedness, which is very good. And this reduction relation is confluent and produces unique normal forms. And we prove that by proof techniques from lecture notes by Tobias Nipkow that you may know. That's the first bit. Then the second bit is counting reduction steps, so we can see we are actually making things better. And what this diagram here is showing is that if we start at the bottom, if we start with the term e and we do call by value steps to a value v in I steps, well, that would be one thing we can do, but we can also run specialization-safe reduction to a term e prime. So that would be like partial evaluation. And at that point, we will only have I prime steps in call by value left to a value. And it's a theorem that I prime is always less than equal to I. So it's saying that specialization-safe reduction can only make things better. And indeed, if our way of counting time is called by value steps to normal form, then our reduction relation from the previous page is specialization-safe. This diagram theorem we proved using a proof technique we found in a paper by Alex Simpson. So now we can hack Boneson's partial evaluator. So you have his partial evaluator in the first line and ours in the second line. And so what we do is we start with a raw lambda term, we annotate maximally, then we run specialization-safe reduction to normal form, and then if there are any annotations left, we erase them and make sure that we get a representation of all that. And that partial evaluator is Jones-optimal particularly for counting call by value steps and using Monson's self-interpreter that you saw on a previous page. So that's as much as we did by math. And let me just do one example here of showing that really this works. So here we're doing church encoding of programs like Torben Mogensen did, and we're running his self-interpreter. And we're going to specialize this just using specialization-safe reduction. And indeed, using even rules that does not include rule 5, we get to the expected result. And then we could start to play around and instead use another kind of encoding that's called, certainly I call it Mogensen-Scott encoding. And in that case, if you want to do the same kind of slide, you would end up needing rule 5. That's a key reason why rule 5 is. Okay, so that's what I wanted to say about Jones-optimality and specialization-safe reduction. Now let's turn on how to type check all this. So we had this paper, Matt and I, in POPL 2017, where we had an extension of f omega with recursive functions and intentional type functions. And so we used that. We had all our software lying around from the days of artifact evaluation, and we start programming the partial evaluator. And the first thing we program is a way of type checking something we need to type check the representation of terms. And so what you have here is a type function that is supposed to be used for mapping the type of a term to the type of the representation of the term. So we call that type function exp. And there's a whole bunch of stuff here, and really what it has is one entry for every construct in the language, and one has to really be an expert f omega programmer to get this right. So that we have Matt as our expert in the project. And then we get the theorem we want. If an expression E has type T, then the representation of E has type expression of T. And so that works well. And you notice that the type of a representation is derived from the type of the term. And in this setting here, untyped type programs cannot be represented. All the represented programs are typed programs. And so then we can start programming the partial evaluator itself, and there's just a wrinkle here I want to mention. If you go to the Bible on partial evaluation by Neil Jones, Carsten Goman, Peter Sestoff, from back in the day, in chapter 16, they have this type listed there as the type of the partial evaluator. If you glance at it, it kind of makes sense. But you notice the second argument is A. And the reason it's A is that those people have base types in their language. And we don't have that. We have pure lambda calculus. So instead, we go with a partial evaluator of a different type, which we got from a paper by Karet, Kisilyov, and Shan. And so you notice instead of A, there's X of A, and it works beautifully. And the key point I want to mention is that in the book, they show that this type supports type checking all the Futamura projections, so that's good. And similarly, one can use the Karet, Kisilyov, Shan type to show that that one also supports type checking all the Futamura projections. So this is all good. So now, experiments. So we've done type checking, and so now finally here comes some experiments. So until now, I have been talking about this church encoding that Mogensen had, and I've been talking about the self-interpreter that he wrote, and it was all call by value. Now we're going to broaden out and see if we can get this partial evaluator to work on more cases. We're going to have a tagless final representation that also comes from the Karet, Kisilyov, Shan paper. We're going to have a Mogensen-Scott encoding that I alluded to. Both of these are parametric high-order abstract syntax representations in the sense of Adam Shipala. And finally, we have a de Bruijn index kind of representation as well. And then for each of these, we're going to have three sort of underlying semantics, if you will, three different ways of measuring time. Call by value, normal order, memoized normal order. So you can map those to your favorite language that support those kind of reduction orders. And you can see that the interpreters slow things down anywhere from something reasonable like 10x to sort of like much less reasonable, like way above 100x. But that's just the world of interpreters. They do slow things down. So now we're going to do first Futamura projection. And so we're going to specialize for each of the 9 cases, we're going to specialize the self-interpreter to some programs. And in all cases, so we have our benchmark suite. It's very fancy. It consists of the cube function, the factorial function, and Ackermann function. And then we have a whole range of inputs that we try. What you see in the before section up here is 9 lines, 1 for each of the 9 cases on the previous page. And similarly in the after section. So before is Torben Mogensen's partial evaluator doing first Futamura projection, and the after section is our partial evaluator doing specialization-safe reduction. And so what you see is sort of the range of what we got from all the experiments. So sometimes we get a slowdown, sometimes we get a speed up, never more than 2x, but the average is marked by a red mark. And so you can see even on average, we end up with a slowdown in many cases with the original partial evaluator. And then once you go to specialization-safe reduction, you always get a speed up. So the claim that we had as a theorem for call by value and what it was, it actually works for one partial evaluator across all these settings. You never get a slowdown, you always get a speed up. Then we can repeat this experiment for second, third, fourth Futamura projection. Same picture, always get a speed up, never get a slowdown. Okay, so just finally, let me just mention where can we find anything like this in the literature. I wrote to Olivier Danby, and he told me that actually the Similix system that he and Anders Bondorf worked on in the early 90s was Jones-optimal. It was a self-applicable partial evaluator for scheme, and he said it's Jones-optimal. Certainly not typed because it was scheme. But I must say that there's no math anywhere to be found that supports the Jones-optimality, but I know these people worked hard, and I'm willing to take their word for it. So what we have now is the first partial evaluator that is simultaneously typed, self-applicable, and Jones-optimal. And it's easy to implement. If you have a system where you need to control duplication and avoid slowdowns, you can do this too. And I'm in the situation that I'm in an Office of Naval Research program that's starting up this month. I see several PIs in the audience here, and we promised to program a Java partial evaluator, and we are going to build in specialization safety to make it work well. Thank you.
So when you introduced your linear lambda calculus, you said this was your variant. And so what immediately jumps to my mind is, well, I can allow linear variables inside nested lambdas as long as I make sure that that nested lambda itself is only applied once.
Yes.
And so not going that route, is that a question of having a good annotator that can successfully do that? Okay.
So you know what? We know that we need to go further, and we stopped when we got the Futamura projections to work. That was like, okay, we're done. But yes, one could go further. And I know that there are fancy algorithms out there for annotating the linear terms, and I think that for other applications, that would be exactly what we need.
Cool. Thanks.